Chapter 1.3, Complex Numbers. People use the term complex numbers and the term imaginary number interchangeably, but technically there's a distinction between the two. A complex number has the form a plus bi, where a is the real part and bi is the imaginary part. An imaginary number is the square root of a negative number. So if we let I equal the square root of -1, we can see that the square root of -4 can be thought of as I times the square root of 4, or in other words, 2I. In working with complex numbers, it's imperative that the first step is to replace any negative sign under the radical with an I outside the radical. After that, an I performs like any variable. One thing we might want to keep in mind before we start our brief review of complex numbers is the pattern associated with the complex numbers. As we mentioned, I is the square root of -1, or in other words, I. But if we were to square, right, I, that would mean we would square a square root and leave us with just the -1. So I squared equals -1. After that, we can realize that we can take any power of I and change it to some I squared times some other power of I. Since I squared is -1, we would have I squared times I, in this case, -1 times I, or negative I. I to the fourth, we can change to, oh, there, I was trying to make that change this whole time. We can make that change to I squared times I squared. In other words, -1 times -1, or +1. I to the fifth, we can rewrite as I to the fourth, which we see from above as 1 times I, or notice we're back to just I. I to the sixth, we can write as I to the fourth, because that's 1, times I squared, -1, or -1. Look at the pattern. I, -1, I, 1. I, -1, and it continues. I, 1. I, -1, I, 1. So that every fourth power just repeats, meaning I can figure out that I to the 17th must be however many groups of 4 are in here. I divide 17 divided by 4. 17 divided by 4 goes 4 times with a remainder of 1, meaning I can write this one time as I to the fourth times 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 I. 4, 8, 12, 16, 17 I's. But all of these I to the fourth are 1. 1 times 1 times 1 times 1 times I. So I to the 17th equals I. I to the 27th, on the other hand, I could find out by saying, well, 27 divided by 4 is 6 with a remainder of 3. That means there's 6 ones multiplied times itself, I to the fourth times I to the fourth, times I cubed, which is -I. So I can find out easily any power of I if I just keep in mind this pattern. I, -1, I, +1. Okay, let's look at a couple of quick examples on complex numbers. And remember, on complex numbers, this is going to just be a quick review of some basic things we need to remember. First thing when I'm trying to simplify these radical expressions is if there's a negative underneath the radical, my first step must be pull that negative out and replace it with an I, or square root of -1. So same thing here, pull that negative out and replace it with an I. Now after I've done that, an I works like any other variable, recalling that anytime we get an I squared, we can replace it with -1. And then I just have to know my rules or my properties for multiplying and dividing radicals, which we should already know. So if I multiply all this together, I get an I squared, okay, times the square root of 12 over the square root of 3. Well, remember that I squared. Anytime I get an I squared, I can replace that with -1. So I have -1 times, using my properties of radicals, let's put these values together under one radical because 12 divided by 3 is 4. So I have -1 times the square root of 4, but the square root of 4 is 2 for a final answer of -2. So the main thing I have to remember is anytime there's a negative underneath a radical, I pull it out and make it an I. And then after that, I can simplify treating the I like any other variable. However, if we wind up with an I squared, I can replace it with a -1. Okay, in this problem down here, the I has already been taken care of for us. So all I have to do is multiply it out. And remember, whenever it's in the form of an I, it works like any other variable. So to multiply this out, I've got to do the square first, exponents first, right? Hopefully we know the shortcut for multiplying out a perfect square binomial. If we don't know that shortcut, we can continue to realize that I can rewrite this in this format and then do my distributive property here, which you might also refer to as FOIL. But if we don't already know that shortcut, let's try to learn it. We're going to use it multiple times throughout this course. So the shortcut is, I'm going to square that first term, which would give me a 4. I'm going to multiply both of these, everything, together. So 2 times -I is -2I, and double it. That's -4I. And then square this last term. Well, when I square a negative, it's positive. But an I squared gives me I squared. Now don't forget, anytime I get an I squared, I can replace that with -1. So I wind up with 3I times, this is 4 plus -1, so 3 minus 4I, and then just continue multiplying using the distributive property. We get 9I minus 12I squared. Hey, there's an I squared. Don't forget that I squared is -1. So giving me a final answer of -12 times -1 is +12 plus 9I. And it doesn't really matter all that much whether we put the 12 or the 9I first or last. However, this is considered the standard form for a complex number. You've got your real part and then your imaginary part. So your homework's probably always going to want you to leave it in the standard form. But technically, remember, with a plus sign, 2 plus 3, 3 plus 2, it's commutative. The order doesn't technically matter. Unless, of course, the instructions specifically state to leave it in standard form. Okay, one more. Whoops. Sorry, guys. Just as earlier, it was mentioned that you should know your rules for radicals already. If you don't, you better brush up on that. Okay, I also need to realize, because I know about radicals, that I can't have a radical in the denominator. And I is a radical because I is square root of -1. Therefore, I also cannot have an I in the denominator. So hopefully we remember from our radical properties the way to get rid of a radical in the denominator in this format is to use something called the conjugate. In other words, the exact same terms in my binomial, but with the opposite sign. Now, once I figure out what I'm doing to the bottom, I've got to do the exact same thing to the top to keep these fractions equivalent, right? I don't want to change the value. I just want to change the appearance. So on top, I don't have a shortcut here. It's just a multiply out, use my distributive property to get -6 minus 3i plus 8i. 8i minus 3i is 5i. And then plus 4i squared. Oh, hey, there's an I squared again. Remember, anytime you get an I squared, that's a -1. And then on the bottom, this is another one of my special products that hopefully we know how it multiplies out again. If not, we want to keep practicing that until we do. If all else fails, I can go back and use my distributive property like I did here, but I want to recognize these special products. We use them a lot. And this special product, if they have different signs, says you square the first term and you square the last one, and there's always a minus in the middle. And notice we got another -1. So on the top, we wind up with -6 plus 4 times -1 is -4. So -4 minus 6 is -10 plus 5i. And on the bottom, this is 4 minus -1. 4 plus 1 is 5. And then recall that it goes without saying that all fractions have to be simplified. Be very careful about how you simplify. You can only simplify factors, remember. So I'd have to factor out that 5 and make -2 plus I over 5. And now that this is just a multiplication or a factor, I can divide it out for a final answer of -2 plus I. Okay, this was a very quick, brief review of some of the aspects of how to deal with complex numbers. Complex numbers are a radical, so we do need to know our properties of radicals also. Just recall that if you have a negative under a radical, first thing you have to do is pull it out and make it an I. If you have any questions, let me know.